we are going to start module 3 of chapter 9. In this module, we shall discuss Euler's equations of motion. So far, we have discussed rigid body motion. The rigid body motion is a combination of translatory motion and rotatory motion. The body set of axes of a rigid body form a non-inertial frame as they are rotating axes, and with respect to these axes the moments of inertia are steady. So, we need a general scheme with respect to such set of axes to tackle the dynamical problems. So, let us consider the general scheme in this module. In this module, we shall derive Euler's equations of motion. Using these equations, we shall obtain integrals of motion. Next, we shall apply Euler's equations of motion to solve some problems. Then, Poinsott's representation of motion of a rigid body about a fixed point when there are no external forces will also be discussed. Let us obtain Euler's equations of motion. Let a rigid body turns about a point O fixed in both body as well as space. Let O suffix x, O suffix y, O suffix z be the three principal axes of inertia at O, O being the origin. These axes are essentially mutually orthogonal and fixed in the body. Let I vector, j vector, k vector be three unit vectors along Ox, Oy, Oz respectively. X, Y, Z are in suffix. At time t, the body has an angular velocity omega vector. Omega vector has components omega 1, omega 2, omega 3. That is, we can write omega vector as omega 1 into I vector plus omega 2 into j vector plus omega 3 into k vector. 1, 2, 3 are in suffix. So, omega vector can be written as omega 1 into I vector plus omega 2 into j vector plus omega 3 into k vector, and the angular momentum about O can be written as LO vector, O is in suffix, is equal to capital A into omega 1 I vector plus capital B into omega 2 into j vector plus capital C into omega 3 into k vector, where capital A, B, C are the principal moments of inertia. From the previous equation, we get capital A into omega 1 dot into I vector plus capital B into omega 2 dot into j vector plus capital C into omega 3 dot into k vector. We get these three terms from del del t operated on LO vector, where LO vector is the angular momentum vector, omega 1 is the angular velocity along the x axis, omega 2 component of angular velocity along y axis, omega 3 component of angular velocity along z axis. If we substitute omega vector cross LO vector, we get this determinant. In the first row I vector, j vector, k vector. The second row components of omega vector, which are omega 1, omega 2, omega 3. In the third row, the components of angular momentum vector LO vector has been written, which are capital A into omega 1, capital B into omega 2, capital C into omega 3. NO vector has the components capital N1, capital N2, capital N3. So, we can write NO vector as capital N1 into I vector plus capital N2 into J vector plus capital N3 into K vector. Similarly, the other two equations can be obtained. These equations of motion are known as Euler's equations of motion of a rigid body about a fixed point which is O. Now, let us find the integrals of motion. In the absence of external forces, that is, if there are no external forces, please note that the moment of the external forces will vanish. So, NO vector must be 0. Therefore, the components of NO vector, that is N1, capital N1 becomes 0, capital N2 becomes 0, capital N3 becomes 0. Putting these value in Euler's equations of motion, we get these three equations. We have already obtained Euler's equations of motion, just substituted the value of capital N1 equal to 0, capital N2 equal to 0, capital N3 equal to 0. Now, we multiply first equation, that is 9.7a by omega 1, 9.7b by omega 2, 9.7c, that is third equation, by omega 3. And if we add these after multiplication, then these terms will cancel out each other and we get capital A into omega 1 dot plus capital B into omega 2 dot plus capital C into omega 3 dot equal to 0. This has been written here. Other terms cancels each other. This can be written in this way, that is ddt of half into capital A into omega 1 square plus capital B into omega 2 square plus capital C into omega 3 square equal to 0. This expression is nothing but the kinetic energy. We are all aware about it. We have already obtained this expression. So, after integration, we get this equal to constant. That is, we get kinetic energy T equal to constant. As kinetic energy T becomes constant throughout the motion, so we can call it as integral of motion. Next, if we multiply equation 9.7a by capital A into omega 1, please recall that before this we have multiplied first equation by only omega 1. Here we are multiplying by capital A omega 1. Multiplying second equation, that is 9.7b by capital B into omega 2, 9.7c by capital C into omega 3, and adding we get this one, capital A square into omega 1 dot plus capital B square into omega 2 dot plus capital C square into omega 3 dot equal to 0. Other terms cancel each other. This can be written in the following way, that is ddt of half of capital A square into omega 1 square plus capital B square into omega 2 square plus capital C square into omega 3 square equal to 0. Here ddt stands for the ordinary derivative with respect to time t. This on integration gives capital A square into omega 1 square plus capital B square into omega 2 square plus capital C square into omega 3 square equal to constant. If we denote it as this one H0, we get HO square equal to constant. Here HO vector is the angular momentum vector. We have denoted angular momentum vector as yellow vector. Here we just used capital HO vector to denote the same quantity, that is angular momentum vector, about the point O. Capital A omega 1 is the component of angular momentum vector about x axis. Capital B omega 2 is the component of angular momentum vector HO vector about y axis, whereas capital C into omega 3 is the component of angular momentum vector about z axis. Thus, one may conclude that absolute value of HO vector equal to constant. The suffix O stands for about the point O. We just used it to mean that the angular momentum is considered about the point O. That is, magnitude of the angular momentum vector remains constant. This is another integral of motion. So, we have obtained two integral of motion. In the previous module, we have obtained the linear momentum and angular momentum of a rigid body. Also, we have established the torque equation of motion. In this module, using the relation between torque and angular momentum, we have already established Euler's equations of motion for a rigid body about a fixed point. Then, using these important equations, we have obtained the integrals of motion in the absence of external forces. Now, we are interested to apply these equations to solve some specific problems. Next, consider problem 1. A rigid body which is symmetric about an axis has one point fixed on this axis. Discuss the rotational motion of the body, assuming that there are no forces acting other than the reaction forces at the fixed point. As the body is symmetric about an axis, so let capital A equal to capital B. Capital A and capital B are the principal moments of inertia about the transverse axis. Then Euler's equations of motion become capital A omega 1 dot minus capital A minus C into omega 2 omega 3 equal to 0. Please note that there are no external forces. So, capital N1 vanishes, capital N2 also vanishes, capital N3 also vanishes. Since capital A equal to B, so we have substituted capital A in terms of B and get this equation. Similarly, from Euler's equations of motion, we get equation 2, and in a similar fashion we get equation 3. From 3 we have omega 3 equal to constant. If we put the constant as k, then one can write omega 3 equal to k. We have obtained this result just after integrating this one. Substituting this value, that is 5, into equation 1 and 2, we have capital A into omega 1 dot minus capital A minus C omega 2 into k equal to 0. Similarly, substituting in 2 capital A into omega 2 dot minus capital C minus A omega 1 into k equal to 0. As the body is symmetric about an axis, so let capital A equal to B. A and B are the principal moments of inertia about the transverse axis, we have already mentioned it. Differentiating 5 with respect to time t, we get capital A into omega 1 double dot minus capital A minus C k into omega 2 dot equal to 0. Transferring this term into the right hand side, we get this equation, this one. If we substitute the value of omega 2 dot here, then we get this one. Please note that this is a constant. After dividing by A, we get omega 1 double dot equal to this one. This is also a constant. If we put this constant as capital omega square, then we get omega 1 double dot equal to minus capital omega square into small omega 1, where capital omega square stands for capital A minus C whole square into k square divided by capital A square. In a similar fashion, we can get omega 2 double dot equal to minus capital omega square into omega 2. This is a second order ordinary differential equation. Its solution gives omega 2 equal to alpha cos capital omega t plus beta sin capital omega t. Alpha and beta are arbitrary constants. From the initial condition, we can obtain the values of alpha and beta. If initially the body is given an angular velocity in the zx plane, then omega 2 obviously 0, because omega 2 is the angular velocity about y axis, but here we have given the angular velocity in the zx plane. So, omega 2 equal to 0 initially means at t equal to 0. This gives alpha equal to 0. Therefore, we have omega 2 equal to beta sin capital omega t. After substituting this value, we get this equation, that is capital A into omega 2 dot equal to capital C minus A into k into small omega 1. Differentiating omega 2 with respect to time t and substituting here, we get this equation. From this, we can obtain omega 1 as this. Putting the value of capital omega, we can get omega 1 equal to small beta cos capital omega t. Therefore, small omega 1 square plus small omega 2 square equal to beta square, which is a constant for all time t. We have already proved that omega 3 equal to constant. Therefore, the angular velocity in the xy plane is constant. Omega 3 is the angular velocity about z axis, that is in xy plane angular velocity is constant. Next problem. A body moves under no forces about a point O. The principal moments of inertia at capital O are 6 capital D, 3 capital D and capital D. Initially, the angular velocity of the body has the components small n, 0 and 3 into small n about the principal axis, so that at any later time the component of angular velocity about y axis, that is omega y suffix y, is given by omega suffix y is equal to minus root 5 into small n tan hyperbolic root 5 small n into t, and that ultimately the body rotates about the mean axis. That means mean axis means y axis, as we are considered x, y, z. So, y is the mean axis here. From Euler's equations of motion, we get these three equations. We have just substituted the principal moments of inertia in the Euler's equations of motion, and since there are no external forces, so right hand side becomes 0 in each equation. Multiplying equation 1 by omega x and equation 2 by omega y divided by 5 and adding, we get this equation. We have just multiplied in such a way so that the product term vanishes, that is this term cancels with this one. In a similar fashion, multiplying equation 2 by omega y divided by 5 and multiplying equation 3 by omega z divided by 3 and adding, we get this equation. Here also we wanted to cancel these product term. That is why we have multiplied by omega y by 5 and omega z by 3 to eliminate these product terms. Integrating equation 4 and using initial condition, we get 3 into omega x square plus 3 divided by 5 into omega y square, which is constant. We get the value of the constant as 3n square using the initial condition. Please note it. From this, one can obtain omega x in this way, just after transferring this term in the right hand side and taking the square root and dividing by 3, we get this result. Similarly, integrating 5 and using the initial condition, we get this result. From this relation, omega z can be obtained in a similar fashion, that is after transferring this term on the right hand side, multiplying by 3 and then taking square root, we get this result. Substituting omega x already obtained and omega z into equation 2, we have this equation. On simplification, this becomes this one. Omega y dot can be written as ddt of omega y. This can be written as minus of 5n square minus omega y square divided by 1. For integration purpose, we have put it in this form. Then integrating between t equal to 0 to t, we get when t equal to 0, omega y becomes 0 because it is the initial time, and at t equal to t, omega y is omega y. So, the limit of integration is omega y equal to 0 to omega y d omega y divided by 5n square minus omega y square equal to minus t, or taking minus t on the left hand side, we get after integration that this is equal to 1 divided by root 5 into n tan hyperbolic inverse omega y divided by root 5 into n. On simplification, omega y can be written in this way. Putting the value of omega y in the expression of omega x, we get this result, which on simplification gives n sec hyperbolic root 5 nt. Similarly, omega z can be obtained. We know that sin hyperbolic x can be written as e to the power x minus e to the power minus x divided by 2, whereas cos hyperbolic x is equal to e to the power x plus e to the power minus x divided by 2. If x is very large, then sin hyperbolic x is nearly equal to e to the power x. Similarly, cos hyperbolic x is nearly equal to e to the power x. So, after dividing, we get tan hyperbolic x is nearly equal to 1 for large x, and sec hyperbolic x tends to 0 when x is very large. Therefore, as t tends to infinity, that is for large time, then x, which is the displacement, it is also large. Therefore, in that case omega x tends to 0, omega z tends to 0, but omega y tends to minus root 5n. Omega y is the angular velocity about the mean axis. So, the body ultimately rotates about the mean axis. Now, Poinsore's representation of motion of a rigid body about a fixed point when there are no external forces. The equation of momental ellipsoid at O referred to the principal axis of inertia is capital A into x square plus capital B into y square plus capital C into z square equal to capital M into epsilon to the power 4, where capital M is a constant having the dimension of mass and epsilon is also a constant having the dimension of length, so that both sides of this equation are dimensionally consistent. Let us check it. Capital A is the moment of inertia. So, this is of the form mass into y square plus z square. So, in this term we have the dimension of mass m into dimension of length its power 4 y square into x square, that means dimension of length and its power 4. So, here we get on the right hand side dimension of m, and as epsilon gives the dimension of length, so mass into dimension of length is 4. In similar way, other terms gives the same result, that is we have mentioned that both sides are dimensionally same. Let the instantaneous axis of rotation meets the momental ellipsoid at capital P function of x y z, the coordinate of P is x y z, where OP vector is the radius vector r vector and omega vector is the angular velocity vector. Therefore, the direction cosines of the axis of rotation are omega x divided by omega, omega y divided by omega, omega z divided by omega. Omega x, omega y, omega z are the components of omega along x, y and z axis. Again, the axis of rotation has the direction cosines x divided by r, y divided by r, z divided by r. So, they are equal, we get this type of equations. From this one can obtain x, y and z, which has been written here. Since P is a point on the momental ellipsoid, so the coordinates of P, that is x, y, z, must satisfy the equation of momental ellipsoid. Therefore, substituting the value of x, y, z in the equation of momental ellipsoid, we get this result. If we multiply both sides by omega square, then left hand side becomes capital A into omega x square plus capital B into omega y square plus capital C into omega z square, which is the 2 into kinetic energy, that is 2t, and right hand side becomes capital M into epsilon to the power 4 divided by r square into omega square. Please note that omega x means here x stands for suffix, omega x is the angular velocity about x axis. From this relation one can obtain omega given by the relation 9.10. But we know that kinetic energy T is constant, we have already proved it. So, omega divided by r equal to constant, because T is constant, capital M is constant, epsilon is also constant. So, square root of a constant quantity is also constant. One can conclude that omega is proportional to r. The equation of the tangent plane to the momental ellipsoid at P, if we take capital X, capital Y, capital Z as coordinate axes, is capital A into capital X into small x plus capital B into capital Y into small y plus capital C into capital Z into small z equal to capital M into epsilon to the power 4. The direction cosines of the normal to this plane are proportional to capital A into small x, capital B into small y, capital C into small z. That is proportional to capital A, we have substituted the value of x here. Substituting the value of y, we get this one. Substituting the value of z, we get this one. That is proportional to capital A omega x, capital B omega y, capital C omega z, since omega and r are proportional. Therefore, the tangent plane is an invariable plane and so fixed in space. The perpendicular distance of the tangent plane from the origin is small p equal to capital M into epsilon to the power 4 divided by square root of capital A square into x square plus capital B square into y square plus capital C square into z square. This can be written in this way, squaring p square and then reversing, we get this result. Putting the value of x, we get this result. If we take out omega square from this bracket, we get this result. Now, this is the HO square, we have already obtained this result. Putting this value as HO square, we get this one, and we have already obtained the expression of omega square. We have substituted this. Thus, we get small p equal to this one, which is a constant, because m constant, epsilon constant, t constant and HO also constant. The tangent plane at P is fixed in direction, which we already proved it, and is at a fixed distance at O and hence fixed in space. As the rigid body motion is a combination of translatory and rotatory motion, so in such type of motion we need a general scheme to solve different types of dynamical problems. In this module, we have obtained Euler's equations of motion, which are very helpful. Using these equations, integrals of motion have already obtained, and Poincaré's representation of equation of motion of a rigid body about a fixed point has also been discussed.